In this video, we're going to be taking a look at instantaneous velocity. But before that, we're actually going to take a look at average velocity once again. Take a look at the plane. It starts in Boston, and when you're flying 10,000 miles, you're bound to be speeding up, slowing down, speeding up, slowing down. So your velocity is definitely not constant. It's changing. But you could find the average velocity through the trip. So if we know the displacement is, say, 10,000 miles, the velocity, the average velocity, is the change in position, 10,000 miles divided by the time. So 500 miles an hour. That is your average velocity. So definitely during that time, you probably traveled at 450 miles an hour or 550 miles an hour or 600 miles an hour. So your speed and velocity was definitely changing all over the place. Now, here's a core question. How do you find an exact velocity at an exact time? Because think about the plane. The plane is not staying at the same velocity for every second during those 20 hours. It's changing its velocity all the time. Since the plane is changing its velocity all the time, it begs the question, what is the velocity at a very exact moment? So that's what instantaneous velocity is. So take a look at the word instantaneous. We want to know the velocity at a very particular, exact instant in time. Not over an average of 10 or 20 or 30 hours, but at a very particular narrow point in time. Because think about this. If you have a speedometer, the speedometer is telling you your speed. It's a speedometer, right? Your speedometer is telling you your speed at a very, very particular point in time. Otherwise, if your speedometer told you your speed, average speed over the last, say, 10 hours, you could be going down the highway at 60 miles an hour, but your speedometer would be reading 20 miles an hour because that would be your average speed over the last 10 hours, or vice versa. It would not be very helpful at all. So sometimes you want the average, but other times you may want to know the instantaneous quantity, the value of the quantity at a very, very exact point in time. So a speedometer is the classic case because it tells you your speed at that exact moment when you're looking at it. What do you think? You may want to pause the video as I ask these questions. The most accurate representation of instantaneous velocity is found through A or B. It is B, because you want to measure over a very small distance. And that's going to become more clear in a moment. Average velocity is usually found by A or B. And that is A, measuring over a large distance. Is it possible to exactly measure instantaneous velocity? True or false? And the answer is, it's false. You can never ever measure something exactly in science. There is always a little uncertainty in your measurements. You can certainly minimize the uncertainty, but it's always there. So when you look at your speedometer and it says exactly 80 miles an hour, yes, it is very accurate, but it could be 80.001 miles an hour or 79.9999 miles an hour. So that's the thing about instantaneous. It's a generally it's a very accurate representation, but it's never exact. But still, it's so close for our work that we can consider it fairly exact. Instantaneous velocity can be considered an average velocity, true or false. That is actually true. It may not seem like it, like average and instantaneous seem like different things, but to measure, to find any velocity, it's still going to be a distance over a time. So an average velocity usually measures over a large span, whereas instantaneous it's more advantageous to measure over a shorter distance. Let's take a look at this. Say you're driving down the road and you have the sensors in the road and it's measuring your speed. And let's say you are driving over the speed limit and you shouldn't. So most people, realizing someone is watching their speed and they're going over the speed limit, most people would slow down. Now, take a look at the car. We have sensor A and sensor B. There is a distance of 100 meters between these two sensors. So 100 meters is a fair bit of distance. That is 328 feet. You can definitely slow down in 328 feet. So if we were trying to get your velocity the very moment you went over the first bar, well, it's not going to be accurate at all, because what this is really measuring is your average velocity over a very large span of distance and time. So how can we make this more accurate? How can we make it so that if someone is truly speeding, they can't slow down and ruin the calculation? How can we make it so there's no possibility that once the person went over the first sensor, you really can't slow down to change your average speed? Well, what you can do is I can put the two sensors closer together. So take a look at that, 1 meter. So generally you want the distance to be fairly small, because if you go over the first sensor and second sensor, yes, you may slam on your brakes, but the distance is so small that you're not going to be able to really change your velocity or speed quickly at all. So when the two sensors are very close to each other, it's more representational of the instantaneous speed, opposed to, say, when the two sensors are very far apart. To calculate the instantaneous speed, you can just say the instantaneous velocity is the little distance x divided by the time it takes. Now, here is the thing. You generally do want the measurement distance to be fairly small, because you don't want an object to be speeding up or slowing down during that interval. But at the same time, you don't want to make the distance too small, and there's a reason. It's because I can do a really good job of measuring, say, a meter fairly well with fairly low uncertainty. But let's say you are measuring something really small, like I'm trying to exactly measure 2 millimeters. Well, I can measure 1 meter fairly well. But if someone asked me to measure 2 millimeters, I could do it, but it's such a small little distance, the uncertainty is incredible. So sometimes you definitely want the distance to be smaller, but not so small that you actually have trouble having certainty about your measurements. So let's take a look at this. You see a car moving forward, moving backwards over time. Now, to find the velocity, we just simply need to pick any 2 points. But this finds the average velocity between these 2 points, because you can see the car is definitely moving forward, then moving backwards. So this just gives you an average. If you want to be technical about it, this line, this red line with the 2 red dots, this is called a secant line. It's passing through our data. Now, if we bring these 2 dots closer together, so look at the red line, now look at the orange line. See how the dots are closer? And now let's make it even closer. So of these 3 lines, the green one is the best representation of the velocity of the car at that first point. It is because the closer the dots are together, the better the representation of the instantaneous velocity. You just get into some trouble in practical real life, because you can't measure something infinitesimally small. You can only make measurements so small, after a certain point it just becomes undoable. So the green slope represents is the closest value to the actual instantaneous velocity. So that is it. Average velocity is the average over a larger distance over a larger time, whereas instantaneous velocity generally is a fairly small distance done over a fairly small time, because you really want to get the value at that exact moment. And that's it for this video.